Hello, today I want to talk about a proof of this characterization of diagonalization that I mentioned in a previous lecture. So what we're going to try to prove is the following important theorem, that an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. And let me write the eigenvectors as v1 through vn. Okay, so that's what I want to prove today. Now remember that diagonalizable means that A equals P times D times P inverse for an invertible matrix P and a diagonal matrix D. Okay? So let me give you kind of the idea, at least, of a proof. Okay, so the main maybe observation here that I'll write down here before I even say anything about the statement is that recall that if P is an n by n matrix, let's say with columns v1 through vn, so eventually they're going to be related to these eigenvectors, but for now just think of them as, anything. They're the columns of this matrix P. And if D is a diagonal matrix, again, just think of this as a arbitrary diagonal matrix. Later they're going to have something to do with eigenvalues, but for now just a diagonal matrix. Then if you take A times P, well, that's A times, what we said is that P has this form here. P is this matrix here. And as you know, when I take a matrix times another vector, that gives you a matrix times another matrix, that gives you a new matrix whose columns are just the matrix times vectors of those columns. So the first column of the new matrix will be AV1, then AV2, and all the way up to AVN. And you can also check that if I take P times D, so if P is this matrix here and I'm taking it times a diagonal, you can check that this will be a matrix whose columns are lambda 1 V1 as the first column, lambda 2 V2 up through lambda n Vn. Okay, so this is just a general fact about matrix multiplication, that when you give me a matrix P and a matrix D, well, this is just matrix multiplication. If D happens to be diagonal, you actually get this nice formula here. So now let's go back to the theorem. If I know that, now let's assume that A equals P, D, P inverse. Okay, so if you're assuming that the matrix is diagonalizable, I want to show you that that actually implies you have n linearly independent eigenvectors. So what I want to show is that I want to find n linearly independent eigenvectors. That's what I'm hoping to prove, or I want to show that if I have this, then I get these eigenvectors. Well, then what we have is that if A equals P D P inverse, and I can multiply on the right by P, and I get AP equals PD. But what is AP and PD? That's what I just wrote here. So that's implying that, AV1, the first column has to equal the first column of this guy. If this matrix AP equals PD, then AV1 equals lambda 1 V1, AV2 equals lambda 2 V2, etc. Lambda AVN equals lambda n Vn. And I'm done. I've got n eigenvectors. Now, why are these linearly independent? Well, note that we're assuming that P is invertible because there's a P inverse here. What that implies is that this collection, remember P has the columns given by V1 through Vn. If P is invertible, then this is a linearly independent collection. So we're done. We've now, assuming that we have A equals P D P inverse, we've cooked up a collection of eigenvectors. That's what this is saying. And since P is invertible, that will be a linearly independent set. Okay? So we have one direction of this theorem that says if you're a diagonalizable matrix, then you've got n linearly independent eigenvectors. So what we have to do now is assume that we have A has n linearly independent eigenvectors. Okay, well, let's say that they're called V1 through Vn, and with eigenvalues, corresponding eigenvalues, lambda 1 through lambda n, then what do I have? Well, again, if I go back to my kind of scratch work here, I know that what this is saying is that this implies that AP equals PD, because if I make a matrix of, as above, if I make the matrix P consisting of these eigenvectors, then, this will always be satisfied. Since AV1 equals lambda 1 V1, because I'm assuming they're eigenvectors, this will actually tell me that AP equals PD. So I'll just say as above. Okay. Now, so we're almost there. We have that AP equals PD, but we want to make sure that P is invertible. We're not quite done because we need P to be invertible, but we're assuming, that the collection V1 through Vn is linearly independent. So I should say that as above, what I mean is that the matrix P has its columns given by those eigenvectors. Okay, we're assuming that collection is linearly independent. What that implies is that P, as you know, is invertible because it's an n by n matrix with a linearly independent collection of columns. Therefore, it's a invertible matrix. So we're done. This implies that, in fact, A equals P d P inverse, because we have this, right? We have this P inverse existing. So if I know that AP equals PD, I can multiply on the right by P inverse. So I'll just say what this is coming from is that AP P inverse equals PD P inverse. We know that's true from what we assumed up here, or we concluded up here. And now, of course, this becomes the identity, and we got what we want. Okay, so that proves the theorem that now this direction was assuming we had n linearly independent eigenvectors. It gave us, a diagonalization of the matrix A. Okay, so that concludes the proof. Put a little box there, and we'll see you next time.